Okay, we start in 1 minute. Okay, thank you very much everyone for attending. I'm Ricardo Chacartegui. I'm professor at the University of Seville, and I am the coordinator of the SOCRACES project. In the Info Day of today, we are going to present a global overview of the SOCRACES project. It has been a 4-year project, and we will make a complete analysis of the experiences that we have had, main results, and the pathway we have followed. The SOCRACES project, Solar Calcium Looping Integration for Thermochemical Energy Storage, it's a project developed within the CSP area in which we try to analyze, to gain knowledge, and analyze the feasibility of the concept of using one of the most abundant material in the Earth's surface, the calcium carbonate, for using the reversible reaction of decomposition of calcium carbonate in calcium oxide and CO2, and storing the products for later on join them again and having a release of the stored energy. Well, to put in context, well, the CSP main research lines are here presented in this slide, and they can be grouped in 3 main blocks. Of course, many other classifications can be done, but cost reduction, improving dispatchability, and environmental sustainability. Our project, SOCRACES, is aimed to the part of dispatchability, providing a large an energy storage capacity based in a non-toxic, abundant material. We base our concept in the calcium carbonate decomposition in calcium oxide and carbon dioxide. Energy is stored breaking the chemical bonds, and when heat is required, we mix again these products to produce calcium carbonate. Sorry, there is some microphone open. Thank you. So the concept was first presented in this paper of Applied Energy in 2016, in which we presented this layout, in which we have that the heat of the sun is used for breaking the calcium carbonate bonds, and where we present the block of charging using the solar energy, storage of the products, the calcium oxide and the carbon dioxide, and when the heat is required, we have the discharge power generation joining the calcium oxide and the carbon dioxide to create again calcium carbonate, releasing energy, and again dealing with the products, the calcium carbonate and the non-reacted calcium oxide. Which are the advantages and opportunities? If you have seen some of the previous published papers related to the project or in previous presentations, we repeat it, I will go relatively fast through them. Well, it has a high energy density. Here you have represented the turning temperature and the volumetric energy density for different pairs. But you can see how the calcium carbonate decomposition, the calcium oxide CO2, they have a high volumetric energy density, the material, and a turning temperature around 900 Celsius degrees. It also has the advantage that in the part of storage, this storage can be done under different strategies. It can be done at ambient temperature for seasonal storage, then minimizing the thermal losses, parasitic consumption of auxiliaries, or also it can be with a different strategy developed for daily operation. Can be done under different criteria, different configurations, can be obtained with different global efficiencies, with different technological approaches. It is based, well, one of the most important characteristics of this concept is that it is based on abundant and stable materials. Limestone, dolomite, they have low price, they're abundant and widely available, and they are non-hazardous or highly contaminant. These are characteristics for the large-scale deployment of energy storage systems. On the side of the discharge, we have heat release. We have that depending on the pressure on the carbonator, we can have delivery temperature very high that allows the integration of advanced power systems like supercritical carbon dioxide cycles, but also in different of even to higher temperatures, even gas turbines. The behavior of the carbonation will depend on the temperature in the reactor. Here you see the reaction rate depending on the pressure and how it changes clearly depending on the carbonator temperature. This is an important issue that affects to the design. It will be highlighted later on this webinar. Also considering the direct and indirect integration, we have that we can use directly this excess CO2 in the carbonator as heat transfer fluid and evolving through the turbine in a direct integration, then avoiding the use of additional heat exchangers for the power cycle, but with challenges regarding the integration and dealing with the granular media separation. Or this is a direct integration, but also it allows the indirect integration in which heat exchangers are provided between the heat release in the carbonator and the power block. It allows the integration of well-established technologies as Rankine cycles, also externally fired gas turbines, or, for instance, the supercritical CO2 cycle still under development. Regarding the advantages and opportunities, we have that materials and equipment are used at an industrial scale in many of the required parts of the system. Many of the equipment is already used in cement industry. The type of reactors, entrained flow reactors, have been proved at industrial scale in other applications. So an important part of the equipment to be used at industrial scale is already available, or at least the knowledge for the development. The challenges: we have a high temperature receiver, and if we are operating at ambient pressure, we will need over 900 Celsius degrees. Now, but also you can consider that it's a closed loop. Different pressures can be used, so I will show later on other opportunities for working at more reduced temperatures, or in other combinations to reduce these high temperature requirements. If we go to these high temperature requirements, the size of the power plant, the solar power plant, will be conditioned, and probably we will need smaller power plants, not thinking 100 megawatts, but in order smaller to reduce the optical losses, increasing the optical efficiency. Besides, we have to consider particles residence times, thermal gradients control, and how would be the continuous operation. Regarding the alternative for reducing the calcination temperature, we have tested within this project the effect of steam calcination. Today we will have a presentation related to the relevant effect and how it reduces drastically the temperature in very affordable temperatures. How also helium calcination also is a very promising option, or very interesting option, and also how affects the vacuum calcination. All is related to the CO2 partial pressure. This here you have the equilibrium. Here you have represented the pressure, equilibrium, and here the temperature. And this is the curve, the equilibrium curve between carbonation and calcination. Other main challenge is the multicyclic calcium oxide conversion. The experiences obtained in the carbon capture and in different experiments at laboratory, we have that there is a deactivation. Of the material with the cycles. So, and what we have studied in this project is how this deactivation, that is highly depending on the design condition of reactors, materials, and processes. And we have proved here, for instance, in this paper, how the calcination under low CO2 pressure enhances significantly the calcium looping performance, avoiding some of the phenomenon, or avoiding or mitigating some of the phenomenon that make the activation of the material. Summarizing, we have calcium oxide precursors with low price, wide availability, hardness, carbonation for power generation or for generating heat in industrial processes can be obtained at high temperature, so it allows high efficient generation of electricity or high efficient industrial processes. Reactants and products can be stored at ambient temperature, depending on the strategy. If we want seasonal energy storage or daily energy storage, different storing temperatures will allow different cycle integration. We have a high energy density there to maximize storage capacity, and materials and process equipment, most of them are well known in large industries like the cement industry. Regarding our SOCRACES operation conditions, we are going to a technology readiness level 5. And what we are trying to demonstrate is how are at these non-laboratory conditions under a higher scale of flows and masses, how is the behavior of the material, how the reactions are, and how the control the designs affect to the different processes. So we, for instance, we have studied how affects to the carbonation, the partial pressure of CO2, or how affects to the calcination, this partial pressure of CO2, regarding the level, the degree of development of the different reactions and processes. What we identify is that operating at in high concentration of CO2, going not necessarily pure CO2, but high concentration, we have that the level of deactivation of the material is clearly different to the one obtained when we have atmospheres, mostly with air. We have that this difference in behavior allows to deal with a more reduced amount of materials and then easing the design, reducing the requirements for replacement, and then showing a high the competitiveness because of the reduced cost and feasibility of the technology compared to designs based or potential designs based on the CO2 capture conditions. This is an important result related to this project. The objective of our project, we will try to show the level of accomplishment we have had in the following presentations. Well, the SOCRACES global objective is to advance in the knowledge of the calcium looping for thermochemical energy storage. We will develop, or we have developed, prototypes of different components. We have studied their integration and their performance. All the experiments, all the activities that we have done are oriented to generate new knowledge about the whole calcium looping process, equipment, materials, reactions, transport, and so on, in order to identify and solve the challenges for the development of other scale equipment to advance to the commercial situation. We have analyzed the material, reaction, systems integration and control, engineering and construction, a big challenge, and the different issues related to the specific systems development. Along these 4 years, we have developed new concepts regarding solar cyclone calciner, donor gravity closed loop calciner, or downer closed loop carbonator. We have spent around 2 years approximately to develop models, analyzing different designs, and within the constraints that we had, we finally go to specific designs for a prototype conceived to get the maximum information about reactions, processes, and equipment. This design, or these designs, is not a beta version of a scale-up system, but is specifically conceived to get the maximum information regarding these parameters, reactions, processes, control, design, to take it into account for a potential scaling up if it happens. So it's not a beta version of a power plant, of a real energy storage system, but in a smaller size. No. All the systems have been conceived to get the maximum information for a potential scaling up and to resolve potential issues, potential problems, or challenges. Here you have how it looks, our prototype, how the different parts are related. Here you have the calciner, cyclone calciner, the vertical calciner. Here you have the carbonator, downer carbonator. Here the power block, the integration between them. Okay. After many challenges, many of them shared with many other colleagues, the pandemic and the problems for constructing and direction of the pilot plant, but not only that, also to understand how everything works, to understand how to solve issues that we have learned when we start to operate the plant. Finally, the pilot plant we were able to operate it and to obtain results. So here, just because it's nice for the nice looking, here you have some thermographies in different parts of the plant operating. And the plant provides results. Not immediately. We have many issues, as you can understand. First of its kind, the most important components. So until we understood completely the processes, the operation, and so on. But here you have an example, for instance, of a sequence of tests, and here you have how is the calcination degree that we have obtained with the cycles, and how is the carbonation degree with the cycle. They are as good as the ones obtained previously in laboratory. So the difference is that here we are dealing with 20 kilograms, 15 kilograms per hour, instead of 1 gram in a closed environment per. And based on these very good results, we are really happy with them. But please be aware that not always happens. We have had a strong, a very hard pathway until get them. Based on these very good results, we have combined these results with our models to predict the performance at a commercial scale, thinking on 50, 100 megawatts plants, and with this result regarding materials and reactions, and considering how it affects to the design of the systems. So we predict a very competitive technology that is below the 9 cents of euro per kilowatt hour. So really competitive global system with other systems. At least at the same price, in the best range of the prices of current commercial technologies, but with the advantage of the other characteristics previously presented. Well, it has been a 4-year journey. We have had many stages from what is the concept, advancing on the concept, the design parts, then the components construction, then erecting the pilot plant, then operating with the plant, and now with this info day until the end of December, we still will follow with the project and we will think of future steps together. All the information, you have it in our website, also in the LinkedIn component. Not all the information that I've shown is already published, but we hope it will be. But here you have a non-complete sample of publications, papers available, showing the effect of integration and processes, the behavior of materials, effect of components, calcium looping perspectives and challenges, and even evolution to hybrid calcium looping CSP of photovoltaics, or also evolution of calcium looping combined cycle. There are many more papers from different, so please, if you have interest, please go through them, and you can contact the partners for having them or to have more information about it. Well, with this, I present this introduction about the technology, and I would like to share with you now. I would like to share with you a video. Let me see. about the construction. I think it will give you an idea of what we have done. Okay. Please confirm me if you hear correct.
Energy storage is one of the most important challenges for a short-term deeper penetration of renewable energy sources. SOCRATCES is based on one of the most promising thermochemical energy storage systems, the calcium looping process, CAL, which uses limestone, one of the most abundant materials on Earth. Solar power is concentrated in the receiver to provide heat for the decomposition of calcium carbonate. The products of the reaction are stored at ambient temperature for hours, days, or even months. When energy is demanded, the calcium oxide and CO2 streams react to obtain again calcium carbonate, releasing the stored energy in the reaction. SOCRATCES is an integral and multidisciplinary approach where different knowledge areas are involved.
SOCRATCES aims to demonstrate a novel concept of thermochemical energy storage. It uses one of the most abundant materials on Earth. It is based on the reversible reaction of decomposition of calcium carbonate into calcium oxide and carbon dioxide. Heat is provided by the sun. High temperature heat is recovered when the products join. This heat can be used in high-efficiency power cycles or in industrial processes. In SOCRATCES, we are constructing a prototype, the first of its kind, in which we try to demonstrate, identify issues and solutions of the technology and the concept for evolving towards the commercial level.
We are on top of the calciner right now. Down there is the heliostat field, which reflects the solar power into this secondary concentrator, which is composed of 4 parabolic mirrors, which have the focal point inside the aperture cavity of the solar receiver. Here, an annular chamber receives the calcium carbonate along with a CO2 stream, forming a swirl which homogenizes the temperature, and the calcination reaction takes place. This is the carbonator. Here we have the vessel in which we collected the calcium oxide before in the calciner and put on top of a screw feeder which will dose the proper amount of calcium oxide to the reactor. This is the Carbonator reactor. Here the calcium oxide, previously supplied by the screw feeder, is mixed along with the CO2 stream in a reaction that releases energy. This thermal energy is collected by a bundle of tubes, which conveys to the stream of compressed air, heating the air and delivering the thermal energy to the stirling engine in the power block. The result of the reaction, which is again calcium carbonate, is collected in this lower vessel, which later will be moved to the screw feeder for the calciner tower closing the cycle. This is the power block. Here we have two main systems, the Stirling engine and the main control for the SOCRATCES project. Here we have a local display, which we call HMI, Human Machine Interface. Everything can be controlled from this local display.
Okay, this is a video in which we try to show how is our global prototype and to try to show at least a small part how we work, how we have been working these months. So now to follow with the agenda, we will pass to the presentation of comparison of different integration of calcium looping CSP through multi-objective approach that will be presented by Dr. Umberto Tesio from the Politecnico di Torino. Umberto?
Hello, can you hear me?
Perfectly.
Okay, so I can try to share the screen. Okay, just give me a check if you can see in full screen mode. Okay, I assume you can. Yes, I'm going to talk about a comparison of different integrations of calcium looping CSP through multi-objective approach. This is a work that has been done in my research group in collaboration with Elisa Guelpa and Vittorio Verda. So first of all, as Ricardo already mentioned, there are two main alternatives for the calcium looping integration. First one is the direct and can be realized with an open or closed CO2 Brighton cycle. And the other one, the indirect one, can exploit actually nearly any kind of power block, for example, organic Rankine cycles, steam Rankine cycles, Brighton cycles, or even Stirling cycles. The choice must take into account many different aspects. For example, technical constraints of the components, energy performances, the investment costs, and also the complexity of the layout that can be obtained. So the objectives of our study were to optimize and compare the most promising alternatives for the integration of the calcium looping in the solar power plant. So as assumptions, we have considered a 2 megawatt electrical power output. The discharging time has been set equal to 24 hours, therefore a continuous discharging. And the CAO deactivation is set equal to 0.5. As direct integration, we have considered the closed CO2 Brighton cycle, while for the indirect integration, we have considered the steam Rankine and two different Brighton cycles, one operating with supercritical CO2 and the other one with helium. The characteristics that we wanted to obtain from the optimization process are actually different. And first of all, we want to have the heat transfer processes optimized. And also we want to obtain a synthesis design and operation problem that is as well optimized as well. Finally, we have imposed that no external resources are consumed in order to have a power plant operating in completely only with the renewable resource. Therefore, the most proper method that we have found is the heat set method, which is a method for the process integration. Here we can find in a very compact form the optimization structure. The most important concept is that the charging side section, charging side is optimized separately from the discharging side, and then we make the simulation of the plant with both the charging and discharging section. The process is iterated until the convergence is reached. And as optimization methods, we have used the FNIN search function of MATLAB as well as the pinch analysis, while for the discharging section, it is employed a genetic algorithm, as well as, again, the pinch analysis and the bisection method. So going to the results, here we can find the 4 Pareto curves of the 4 different integrations. If we remove the dominating segments of the curve, we obtained a composite Pareto curve. And starting from the cheapest alternative, we can find that the indirect integration of the steam ranking cycles is the cheapest one, but also the worst performing. Then we can find the indirect integration of the supercritical CO2, then the direct integration, and finally the most performing, but at the same time the most expensive, we have the helium indirect integration. So as final remarks, we can say that higher efficiency, obtaining a higher efficiency in the power block determines lower costs, lower investment costs in the charging sections because of the lower sizes of the components. But this economic advantage is completely overcome by the higher prices that are obtained in the power block itself. And in addition, if the power block is thermally fed directly on the carbonator wall, we obtained in all the cases analyzed higher discharging performances. But at the same time, the presence of the heat transfer on the reactor wall increases a lot the investment cost of the component. So as a final outcome, we can say that if an adiabatic carbonator is chosen for the in the plant layout, then a good compromise between prices and performances can be the direct integration. Otherwise, if it is chosen a non-adiabatic carbonator, it could be an interesting alternative, the indirect integration of the helium Brighton cycle. And with this, I have concluded. Thank you for your attention, and let me know if you have any question.
Okay, thank you very much. Regarding the questions, the attendees can write in the chat the questions, or if they want to if they are very long, they can also ask only for participate. But I think that the best is to advance with the different presentations, and then we compile. I will follow the chat if there is any specific. So, well, my proposal is to advance with the different. Okay. Following the agenda. The next presentation will be made by Mohamed Eusha from TCES-CSP. It's optimization of integration of a stirling engine with the SOCRACES technology. So,
hello everyone. Are you able to see my screen?
Let me see. Yes. Yes.
Okay. So
and we hear you perfectly too.
I'm happy to hear. I'm happy to hear that.
But Eusha, we see the two slides at the same time. No?
Is it okay now? Is it better?
Yeah, better. Yeah.
Okay. So hello everyone. My name is Eusha, and I represent TCES Bremerhaven, involved in this project to design, develop, and construct the power block for the SOCRATES pilot plant. This presentation is principally going to concentrate on optimization of integration of a stirling engine with the SOCRATES carbonator reactor at a prototype scale. Much of it may appear to be similar to the last presentation, but I believe I do have something unique and novel to report in this presentation as well, which you might find interesting. I believe the audience already have been introduced to the basic working principle of the SOCRATES technology, but I would perhaps just mention the part relevant to the power block here. In the carbonator reactor, we allow the discharging process to take place. In other words, the exothermic reaction between the calcium oxide and CO2 takes place in the carbonator, liberating the heat which is taken up by the power block to operate a conventional power cycle. This can be pretty much anything, ranging from a Brayton cycle, as Umberto just discussed, I think, to organic Rankine cycle and so on. For the pilot scale implementation, we thought it would be interesting, if not anything else, to couple the carbonator with a small stirling engine. What is perhaps extremely important to mention here is that the transfer of the heat from the carbonator to the power block is a major engineering challenge itself. It's not easy. The overall efficiency of the power block is affected by the transfer efficiency. And while we perhaps have several critical areas in this concept, in this project, and this is definitely one of them. How is the heat transferred to the power block? So moving on, in direct integration, we have a heat transfer fluid in a heat exchanger picking up the heat from the carbonator, which is then delivered to the power block's boiler heater. Ideally, we would have expected this to be a closed cycle, but you can see here that we have chosen an open cycle. This is for reasons pertaining to economics and ease of implementation, while respecting the objectives of the project. We decided to keep the loop open. This means the air is sent down a spirally wound heat exchanger around the carbonator designed by our colleagues at SERC, and the heat is then released to the stirling engine. So what has to be recognized here is that the stirling engine is not able to produce a very large delta T across the heat exchanger. This means the majority of the heat is actually going to be wasted. We tried to at least address this problem by introducing a plate heat exchanger downstream with a very high effectiveness, if I may be bold to mention here. It's, I think, around 80%, if I'm not mistaken. So this recovers quite a bit of the heat that is sent to the power block. In the case of the pilot scale plant, we obviously had a stirling engine, and an interesting question was whether it makes a difference as to how the hot air is introduced to this heavily finned cylindrical surface area available for heat transfer. We obviously had to introduce an enclosure around the heat exchanger, and the question was how the heat would be fed to the thin surface. So the question was exactly, as I said, how to feed the heating stream received from the exothermic reactor, the carbonator. And what's interesting is the study of the related spatial arrangement of the velocity vector and the heater fins. Thus, it essentially becomes an optimization problem. So this is presented here in this rudimentary scheme that you see here on the right side, the extreme right image. The flow is bifurcated and fed in an opposed blast configuration because we determined from our preliminary CFD simulations that this was the best approach. So if the flow was centrally fed and a central outlet then took the exhaust away, we noticed that there was that the performance was much inferior in that case. So we chose the alternative of the opposed blast configuration. So the simulation, how we did the simulation, you can see that there were basically the simulation, the entire model can be split into two halves here. There is an interaction outside, right outside the right outside the heat exchanger itself, and then of course the engine interior. So the interior of the engine was modeled using a framework involving kinematics and thermodynamics and fluid dynamic model. There are many models available, but we chose the Formosa and this framework. And the external heat transfer. I'm sorry, I think there is some interference here.
No, Eusha, sorry, you can continue.
Okay, do forgive me. So it was possible to write an explicit set of equations giving the heat extracted from the stream by the engine heater, and the heat extracted was calculated as an average over a cycle. So here is a glimpse of the equations used to simulate the heat transfer scenario. These are very basic kinematic equations mostly, included some thermodynamic equations as well. But I don't think there is anything novel or unique here. But what we had to do, this perhaps is quite interesting to our engineer friends here, is that I noticed that the microgen engine, from the data that was made available to us, the performance data, it was difficult to reconcile the data with the available models. The turbulence models, heat transfer models, heat loss models, pressure loss models. And it appeared that with slight changes, if we adapted the models, the pre-existing models, without having to make sweeping changes, just the parameters, if we tweak the parameters slightly, it was able to produce, much more consistent results with the experimental data that was made available to us. So we made these changes to the models available because some of I think it's important to mention here that these Stirling cycle models, they're often developed with just one single engine model in mind. So the Formosa model that I mentioned here, it, for example, is based on I think an engine known as the GPU3 engine, which has considerable configurational differences with the one that we had used. So we felt that it would be foolish to simply go ahead and use these models and expect that there will be consistency, which there wasn't, of course. So we used our models. We optimized the configuration as well, using quite a bit of CFD and implementation in MATLAB as well. And it was found that, so if we go back to this picture here, one that you see on your left, the tangential entries, if we move them gradually towards the center, and it becomes a centrally blast configuration, it appears that the performance is substantially improved. The heat injected into the engine core definitely sees improvement. And this can be seen here in this surface plot that I have plotted here. You can see the left inlet position here and the right inlet position here. So only when they're centrally targeting the engine, it appears that we have the highest heat injected into the core. So when we have the tangential entry, what happens is that the flow has the tendency to stick to the outer wall instead of interacting with the heater fins, which is, of course, undesirable in our case. So this is basically very similar to the Gaussian curve in 3 dimensions. But yeah, so this is something that we found to be very much in line with our experimental data as well. So we, of course, chose, if I may go back a few slides, yeah. So we chose the configuration that you see in the middle here, opposed to radial inlets with axial exit. If we had chosen, for example, the tangential entry, which was initially offered to us by our manufacturer, then we perhaps would have ended up injecting just about 2.5 kilowatts as opposed to 4.2 in the operating conditions shown here. Yeah, which is, of course, a substantial improvement. When you consider larger scale implementations, I think it would be even more pronounced, the difference. So here is, of course, another surface plot which shows the relationship between the engine head temperature, which is explicitly dependent on the power generated by the engine with respect to the mass flow rate and the incoming temperature. And this, of course, seems to be quite beautifully in agreement with experimental data that we were able to generate. So just to finalize, so just to give you a final glimpse of the results here, the comparison between the centrally blast and the tangentially blast configurations, it appears that we have, in terms of thermal efficiency here, it's 18% in case of the tangential entry, about 25% in case of the centrally blast configuration. So this is just a glimpse of the model. On the right, you have the actual setup. The power block has been sent, of course, to Spain. The work has concluded, and yeah, if you have any questions, I would be very happy to answer them. Thank you so much.
Okay, thank you very much, Eusha. Any questions, please? You can, attendants can write in the chat. So as we pass, meanwhile, we can condense all of them at the end of the first block of the info day. Now, the presentation that comes is Carbonation on fine limestone particles for TCES-CSP as affected by acoustic perturbation. That is presented by Dr. Paola Ammendola from the CNR. So, Paola, when you want to.
Thank you, Ricardo. I'm going to share my screen.
Yeah. Let me see.
I don't know. Okay. Okay, good morning. I'm Paola Ammendola, researcher at the Institute of Sciences and Technologies for Sustainable Energy and Mobility of Italian CNR. The work I'm going to present is about the possibility to exploit the high reactivity and multicyclic stability of fine limestone particles in a sound-assisted fluidized bed reactor for thermochemical energy storage in concentrated solar power applications. The calcium looping process has been extensively studied in the framework of both CO2 capture and storage and thermochemical energy storage applications, which differ in terms of operating conditions used in the calcination and carbonation steps. Different reactor configurations can be used to carry out the calcium looping process. Among them, fluidized bed reactors have been considered in the framework of the SOCRATCES project as a possible technological solution, since they can provide height and mass transfer coefficient and uniform temperatures within the bed, thus minimizing the risk of hotspots. In this framework, one of the main drawbacks of the calcium looping system is the progressive decline in the carbonation conversion with the number of cycles, which is due to the calcium oxide deactivation caused by sintering and pore plugging. A possible solution, which has been receiving increasing interest in, is the use of fine particles. Besides these, it should be considered that fine particles can provide better gas-solid contact efficiency due to the higher surface to volume ratio with respect to coarser particles, which positively affects the first fast initial phase of heat passivation to the slow. However, fine particles belonging to group C of Geldart classification of powders cannot be fluidized under ordinary conditions, since interparticle forces prevail over hydrodynamic and gravitational ones, thus leading to agglomeration and channeling phenomena, which in turn hinder the reaction efficiency due to the poor gas-solid contact efficiency. Therefore, in order to overcome these strong interparticle forces, externally assisted fluidization can be used. In this framework, the sound application is able to promote a smooth fluidization regime by a very effective breakup mechanism of the larger aggregates into smaller structures, which can be more easily fluidized, thus maximizing the surface of the sorbent exposed to the gaseous phase and maximizing the reaction efficiency. Therefore, the aim of this study was to enhance the carbonation performance of fine limestone particles in a by means of the application of sound in a fluidized bed reactor. The material, the solvent used in this work is natural limestone supplied by Homia. It is characterized by particle size smaller than 50 microns, and in particular it has a outer diameter lower than 4 microns, confirming that the material belongs to the group C of Geldart classification of powders. All the tests have been carried out in a lab scale apparatus. Consists of a fluidization column made of quartz 40 millimeter in diameter, equipped with the sound generation system. Prior to the calcium looping test, the solvent has been characterized from the fluid dynamic point of view by performing fluidization tests both under ordinary and sound-assisted conditions. In particular, pressure drop curves as a function of superficial gas velocity have been obtained during fluidization tests carried out at different temperature and under the effect of acoustic fields of different intensities and frequencies. The calcium looping tests have been carried out both under ordinary sound-assisted conditions, and the sorbent is subjected to 10 carbonation calcination cycles. Here you can see the results of the preliminary fluid dynamic characterization. In particular, here you can see the dimensionless pressure drop curves obtained at ambient temperature, both under ordinary and sound-assisted conditions. The results show that the fluidization quality is very poor under ordinary conditions. Indeed, the pressure drop curves is very irregular, and the proper fluidization regime cannot be reached due to occurrence of agglomeration and channeling phenomena. On the contrary, the pressure drop obtained with the assistance of the acoustic field is more regular. This is due to the breakup mechanism of the large aggregates inside the bed into smaller fluidizable one due to the effect of acoustic field. The role played by sound intensity and frequency has also been assessed. In particular, you can see here the experimental values of minimum fluidization velocity and fluidizing particle size as functions of sound intensity and frequency respectively. In particular, the sound intensity has a beneficial effect on the fluidization quality. This evidence is due to the fact that increasing intensities, with increasing intensities, more and more energy is introduced inside the bed, thus making the breakup mechanism more and more efficient. Effect and an optimum range can be found. In particular, when the frequency is too high, the sound is not able to propagate inside the bed, and one is so effective. And here you can see the results we obtained on the effect of the reaction temperature on fluidization quality. It is clear that increasing temperatures lead to increased fluidization difficulties, as confirmed by the pressure drop curves shifting to the right. And this result is due to the fact that the interparticle forces become more and more intense as is increased. Notably, the effect of the mechanism to the sound application is remarkable even at the highest temperature, as you can see in this picture taken during experiments carried out at 150 degrees C. Here you can see the results of the carbonation tests in particular. Here you can see the comparison between the CO2 outlet concentration profiles obtained during the carbonation test under ordinary and sound-assisted conditions. In here, on the right, corresponding results in terms of carbonation conversion as a function of time. It is clear that the application of sound is able to remarkably enhance the carbonation performances in terms of larger values of carbonation conversions. In particular, the application of sound makes it possible to maximize the exploitation of solvent reactivity due to the better fluidization quality and in turn the better gas-solid contact efficiency. Finally, here you can see the carbonation conversions as a function of the cycle number obtained during both ordinary and sound-assisted conditions. It is clear that the activation rate is reduced and residual conversion is increased when sound is applied. In particular, natural gas plus natural ordinary under ordinary conditions. On the contrary, when sound is applied, the agglomeration issue is solved and only sintering remains to cause the decline in the carbonation conversion. In analogy to what we done for the preliminary dynamic characterization, we investigated the effect of acoustic parameters on the carbonation performance too. We found that both sound intensity and frequency exhibit on the carbonation performance the same effect as that we obtained from experiments. And so, to conclude, in this study, we investigated the possibility to exploit the high reactivity and multicyclic stability of fine limestone particles in the sound-assisted fluidized bed reactor for thermochemical energy storage in concentrated solar power applications. And in particular, we've successfully proved the beneficial effect played by sound application on the carbonation performance of fine limestone particles, making the sound-assisted fluidization a very promising technological options. That's all. Thank you for your kind attention.
Thank you very much, Paola. The potential questions, please write them in the chat and we will deal with them at the end. There is some noise, sorry. Okay, it was Juan. Well, we will have we will leave the questions at to the intermediate before the break. Now we are going to pass to the presentation Kinetics of calcium looping reactions and the activation of materials that will be presented by Mr. Thanasis Scaltsoyiannes from the Aristotle University of Thessaloniki.
Hello to everyone. Thank you, Ricardo, for your kind introduction. I will share my screen now. So I hope that you all can see my screen in full mode presentation.
Yeah, now we see.
Okay. Yes, I'm representing Aristotle University of Thessaloniki, and I will present to you some of our main results in SOCRATCES project, which are related to the kinetics of calcium looping reactions and the deactivation of limestone. So the project, as you already know, aims at storing the solar energy via the calcium looping reactions. I will not describe any further the whole process, as you can see here, a simple scheme, but I will point out the conditions that the two reactors will operate. The firstly, the calcination, if we have to apply calcination under pure CO2, then high temperatures higher than 900 Celsius degrees have to be applied. And these are temperatures that can be achieved in a solar receiver. And the carbonation will also take place under high temperatures and CO2 partial pressures if we want to have a high temperature CO2 or air.
Thanasis, sorry. Thanasis, it seems that you are mute.
Ah, you don't hear me?
Now yes.
Okay. So I will say in brief what I have told already. So the conditions of the two reactors, I was saying that will be high temperatures for calcination, higher than 900 Celsius degrees, if we want to apply the calcination under pure CO2 stream, and also carbonator will also operate at high temperatures and CO2 partial pressures if we want to have high efficiency in the power block. So the reaction kinetics are very important for the efficiency of the whole process and the efficient design of the reactors. And so we need robust reaction models for this design. Another parameter that is of high importance is the performance of the material. Limestone, as you may know, loses its sorption capacity during the first cycles, and a solution for this has been proposed, which is the introduction of a makeup flow of fresh material to increase the average sorption capacity of the cycled sorbent. So the prediction of the sorption capacity after the first few cycles is very important also for the design of the whole process. So modeling of these aspects of this phenomena is our main goal in our study. Our experiments were carried out in laboratory scale devices. Here you can see a fixed bed reactor unit, which is connected with a CO2 analyzer and a mass spectrometer for analyzing the gas exit of the gas outlet of the reactor. We also carried out experiments in thermogravimetric analyzer in order to apply multicyclic experiments. And here are some characterization techniques that we used. X-ray diffraction, both ex situ and in situ, to track the changes inside the material during the reactions. Also, nitrogen porosimetry is very important as we deal with gas-solid reactions, so textural properties like surface area and porosity are introduced in the models. and scanning electron microscopy also for the morphology of the materials. The materials that we used was a limestone, which is the reference material, but also materials containing an inert phase apart from the active calcium oxide phase, for example, magnesium oxide or zirconia, which has been found experimentally to stabilize and mitigate the deactivation of the material. So let's move on some results for calcination kinetics. Here you can see some conversion time curves for different CO2 partial pressures in the first figure and various temperatures in the second one. We can see that increasing the CO2 partial pressure, the rate decreases as the driving force of reaction also decreases, while increasing temperature leads to an increase in the rate for this endothermic decomposition reaction. So during modeling, we used the grain model where we introduced as input parameters the initial surface area and the porosity of the material from nitrogen porosimetry measurements. And after fitting this equation on each experimental conversion time curve, we derived the only fitting parameter, the specific rate of decomposition reaction. And as you can see, there is a non-linear effect of this rate of the CO2 partial pressure on this rate. And we use this Langmuir type equation to fit this dependence. This is for calcination kinetics, and for carbonation kinetics, we use the random pore model, which is a similar geometrical model than the previous one. Again, we have some input parameters that are related to the surface area and the porosity of the materials. But in this case, we try to expand this model in order to apply for materials that contain an inert phase also, apart from the calcium oxide phase. And this was done by modifying these input parameters. So we introduced new input parameters, which included information for the scanning electron microscopy analysis, X-ray diffraction for the crystallite size of calcium oxide in the inert phase, and of course as well as the surface area and porosity from nitrogen porosimetry. So in the general case, we use these modified parameters as input in the model, and again fitted this equation to the conversion time curves. It's very important to highlight here how fast this reaction is. Carbonation achieves around 60% of conversion under these conditions in only a few seconds. And after fitting, as I said, of this equation of experimental curves, we derived this parameter R, the rate of carbonation. And here we have a first order reaction with respect to the CO2. And we can see that all the materials tested, we tested 4 sorbents with a different inert phase content and are fitted by the same fitting lines, which implies that the modification was done successfully. So the last part is the deactivation modeling, as I said. Here you can see a typical conversion versus number of cycle curve for limestone. As you see, it loses more than 60% of the initial absorption capacity after 10 cycles. From our study, we concluded that porosity of calcium oxide before each carbonation determines the conversion of the material. Also, that calcium oxide sintering affects calcium oxide porosity, while calcium carbonate sintering does not play a significant role in the deactivation of the material. And finally, that changes that happening during each calcination step enhance the deactivation. And more specifically, we carried out in situ X-ray diffraction experiments, where in the first case, the material was first calcined and stayed in calcium oxide form under sintering conditions, while in the second case, the material after the first calcination was subjected to successive calcination and carbonation steps. So here is the evolution of calcium oxide crystallite size in these 2 treatments, and you can see that when the material is cycled, the calcium oxide crystallite size increases after each calcination step. And in this scheme, you can see why this happens. Because after each carbonation step, a portion of calcium oxide remains unreacted, and this acts as a surface for crystallization of the newly formed calcium oxide after the next calcination step. So this phenomena lead to the enlargement of the unreacted calcium oxide crystals and the loss of surface area and porosity, so the deactivation of the material. For these experimental results, these were translated to mathematical equations, and a non-empirical deactivation model is developed, where parameters such as temperature and time of each step of calcination and carbonation are introduced. And you can see here how the model, the solid lines, predict very well the experimental result for deactivation under different conditions. So summarizing, for calcination kinetics, we use the grain model and a Langmuir type equation that can predict the non-linear effect of CO2 partial pressure on the rate. For carbonation kinetics, we expanded the random pore model to apply also for sorbents containing an inert phase apart from calcium oxide. We found the linear effect here for of CO2 on the rate and very fast reaction kinetics. And for the deactivation, apart from calcium oxide sintering, also crystallization phenomena enhance the deactivation of the material, and we developed a model to predict the sorption capacity under different conditions of cycling. So here are some of our publications. You can find more detail of our work, and in conferences some publications during the project. So at this point, I would like to thank you all for your attention. I thank all the partners for the collaboration all these years on behalf of Aristotle University, and of course, I will be happy to answer any question that you may have. Thank you.
Okay, thank you very much, Thanasis. As I said before, we make all the presentations, and then at the end of this first block, we leave room for specific questions, or if someone wants to write already then in the chat. I will take the question from there. So the next presentation is use of steam during calcination in the CaL-CSP process, kinetics and cyclability. That will be presented by, I don't know if it will be Arcenegui.
Hi, Ricardo, I will try to do it.
Okay.
Can you hear me?
Yes, we hear you perfectly.
Okay. I will try to share my screen.
Okay.
So to share the screen?
Not yet.
You have a bad connection, Juan. We can hear you very well.
So, well, the thing is, I'm using the data from mobile. This is not my place.
Okay.
So,
Do you see? We don't see yet your screen, but I think that I have your presentation. So if you want, I can put it,
well,
and you talk over it.
Share my screen. Sorry.
Yeah.
How can I share my screen?
Do you see an arrow at the top, at the right top?
Yes.
There is a button that puts exit or salir.
Yes.
You have an arrow.
I have an arrow down. There is a bar. Now?
It's changing. One moment. Something is changing, but not yet. Let me see.
I will try to disconnect my video. Maybe to improve the connection. Oh, the video is not connected. Can you see my screen? Ricardo?
No, Juan. No,
No.
we cannot see you. We
cannot
cannot see this presentation.
But it's because I cannot, because I'm not sharing it properly, or because the connection?
No,
I don't know.
I think that maybe it's the connection, but we cannot see anything from your computer. Maybe.
Yes.
I don't know.
Juan, do you want me to give the presentation?
I think it's the best, Luis, if you don't mind.
I think now I can. Well, let's just time.
We can hardly hear you, Juan.
Now we see your screen. Now we see, but the sound is really bad.
Yeah, I'm really sorry.
But we see, we see your screen. If you can try, if you want.
Okay. Thank you, Ricardo.
Well,
my name is Juan Arcenegui. I work as a postdoctoral researcher at TCES in the group led by Professor Luis Pérez Maqueda. And today I would like to talk about conducted within the framework of Socrates. In this study, we try to clarify the effect of steam addition on the CaL-CSP process. But we pay attention to the calcination kinetics. I mean how steam influences kinetics, and also how it influences the multicyclic performance of limestone. Here you can a schematic illustration of the experimental setup used in this study. Basically, it consists of thermobalance that allows for steam injection. In this slide, you can also see a micrograph of the limestone sample used in the study. So, as we were interested in studying the kinetics of the calcination, we conducted experiments in isothermal conditions using different amounts of steam in a mixture of steam nitrogen. What can be seen clearly in this slide is that the steam increases the calcination rate. So, as we were interested in knowing the kinetics parameters, we performed a kinetic analysis of using a non-parametric kinetic method. With this method, which consists of obtaining the kinetics parameter without any assumption on the kinetic model. With this method, we were able to obtain the values of the well, the conclusion is that the activation energy decreases with the amount of the steam. So this can explain why the presence of the steam speeds up the reaction. Another interesting aspect of the non-parametric kinetic analysis is that it allows to obtain information about the kinetic model. So we also observed that the kinetic model is modified when a large amount of steam. And to validate our results, we ran experiments under different conditions. In conditions, not thermal conditions, with a linear heating round and we were able to reconstruct the curves of the experiment using the kinetic parameters obtained by the non-parametric kinetic method. So the study was validated by doing this. Well, the interesting thing concerning the application to the CaL-CSP process is that using a steam we can decrease the calcination temperature in order to attain full calcination in a shorter time. So it can be seen here that the use 29% of steam in volume, we were able to decrease the temperature up to 700 degrees. With that, in that condition, we were able to attain full calcination in less than 10 minutes. So, well, we were also, as I said in the first slide, we were also interested in studying how it affects the multi-cyclic performance. So what we found is that the steam also increases the reactivity of the material. So in order to understand this better, we took micrographs of the sample after 20 cycles, shown on the right. And what we found is that the microstructure that we obtain using steam seems to be more open, and we think that this can explain the increase in the reactivity. This kind of structure, more open, will be less prone to pore plugging, and therefore it will allow the CO2 to reach the inner core of the particle. So, as we can say that steam addition decreases the apparent activation energy, that the kinetic model is modified when a large amount of the steam is employed. The temperature needed to attain full calcination can be decreased. Steam helps preventing the loss of in reactivity and creates more open structure resilient for plants. Thank you very much for your.
Okay. Thank you. Thank you very much, Juan. Thank you for the presentation. And following the same criteria that previously, we pass to the next presenter. In this case, it will be Kyriakos Fotiadis from the Center for Research and Technology of Hellas, and he will present Carbonator modeling and construction, next steps. So, Kyriakos, the floor is yours.
Yes, thank you, Ricardo, for the introduction. Hello, everyone. You can see my screen, I suppose.
Yes.
Yeah. Good morning, everyone.
Kyriakos,
my name is Kyriakos, and I'm a mechanical engineer.
Kyriakos, sorry, we see your presentation, but we don't see the presentation now. Now we see the presentation. Thank you.
Now you see it. Okay.
Yes. Okay.
Okay. As I was saying, I'm a mechanical engineer working for CERT, and our contribution for SOCRACES was designing and constructing the Carbonator, a vital part of the prototype. As it has already been said, SOCRACES developed an alternative technology for energy storage. Now, in particular, for the Carbonator, the reaction taking place is the one you can see in the slide here. which is an exothermic reaction. Thus, the produced heat is utilized and contributes in the calcium loop. Now, first of all, the calcium oxide solids are introduced to the reactor. Then the preheated CO2 is entering from the top, and the reaction is taking place. The produced heat is transferred through a helical coiled heat exchanger. The initial step for the designing of the carbonator was the development of a model simulating the physical and chemical phenomena taking place in the carbonator. The model parameters were in accordance with the SOCRATCES project design criteria. Now, the effect of the various parameters on the performance of the reactor was studied, such as the wall temperature, the mass flows of the solids and the gas, and as well as the pressure. And as an output, carbonation up to 60% could be achieved by monitoring those process parameters. Safety and efficiency of the process could be improved. Okay, now after evaluating those results, we concluded that the 4-meter reactor was enough to assure the desired calcium oxide conversion for feeding rates up to 80 kilograms per hour. And here you can see the alteration of the estimated thermal power and the calcium oxide conversion distributions along the reactor's length. And the dependence in the variation of carbon dioxide flows, calcium oxide flows, pressure, and wall temperature. Now, the final design specifications for the reactor are the ones you can see in this slide. The reactor's length is 4.4 meters. The feeding capacities for the solids varies from 20 to 80 kilograms per hour. And also you can see the gas flows for the CO2, the air, and the nitrogen. Furthermore, since the reaction starts at 700 degrees, the preheating of the reactors was a necessity. And for this purpose, 2 furnaces of 44.4 kilowatts each were used, and for the preheating of the calcium oxide solids, furnace of 24.6 kilowatt was used. Now, for the operating temperature was up to 50 degrees Celsius. And another important aspect of the unit is that the upper vessel for the solids in the introduction to the reactor is that it can be used as an independent in situ reactor. Now here you can see the final assembly of the carbonator unit. Now the top vessel containing the calcium oxide solids. So we can see the furnaces for the preheating of the reactors. And those are the 2 parts of the reactor encircled by the heat exchanging coils. Finally, we can see some of the results. First, the conversion was tested here in our facilities in Serth with some preliminary experiments. And we achieved carbonation around to 65% in the temperature of 800 degrees Celsius. And next, it was tested in the prototype in the unit in Seville. And as you can see, the calcium oxide conversion dependence from the reactor's temperature, where for 800 degrees Celsius, the conversion achieved was 77%. While for lower temperatures, the conversion rate drops significantly. That's all from me, and thank you for your attention.
Okay, thank you very much, Kyriakos. Thank you for the presentation. And this was the last presentation of this first part.
Thank you, Ricardo.
This was the first presentation of this first part of the info day. I don't identify any question within the chat. If someone wants to make some question to any of the presenters, please, the floor is open for questions. If don't, now we are with a bit of delay, not very much, but a bit. We can have a break. So, is there any question, or any curiosity, any issue? We can make questions later on after the end of the presentation. So, if no one has any questions, just let me make some as to summarize what we have seen. We have seen in this presentation new knowledge about the effect of the different conditions that could happen inside the reactors, inside the processes. They are new, and you can see that we have seen very, very interesting results related to the effect of temperatures on the carbonation and in the calcination and in the global. We have seen that after the experiment that we have presented here, the member of the consortium, we see that the effect of using sound, using steam, they improve clearly the potential of application with very relevant results related to the decrease of temperatures, one of the challenges that we had, and regarding how is the modeling about the performance in the calcination, in the carbonation, and the potential effect using in the design of components. Also, we have seen in this first presentation, in the last presentation, a very, very interesting results related to how the carbonation affects in a very phase. We have a very, very developed carbonation. Of course, we have seen also how it's clearly it depends clearly of temperature and of the reaction rates to be developed in this small length. For sure, if we go to longer volumes, we will have more developed carbonation even with smaller temperatures. So, if I don't see any questions, but if also, please, no, I see someone. Juan Rincón, please.
Okay, yeah, good morning. Thank you very much for the interesting presentations. Yeah, it's an amazing project. And I have a question for Paola Ammendola about this fluidized bed carbonator, yeah? And okay, yeah, you explain about this or how to improve this channeling phenomena, yeah, not to avoid that. But did you observe it in your experiments, or can you say something about the mechanical properties of the particles? It is enhanced, or the particles will be treated more? Can you shortly say something? Thank you very much.
Okay, thank you.
Okay. I don't know if I understand your question. However, regarding the mechanical stability of the material, we performed some sampling of materials during the tests, and so then analyze them by microscopy, laser granulometry, and so we didn't observe any change in the structure and of material. Moreover, one important feature of sound-assisted fluidization is that the sound application is able to prevent any elutriation of materials from the bed. And so the process is very stable also under from this point of view.
Okay, thank you very much.
You're welcome.
Okay, thank you. Is there any other question? Okay, we can make further questions later on in the second part of the info day. Now, we take a 10 minutes break, and after the break, we will have a presentation regarding the scaling up and Socrates technologies opportunities, another presentation about lessons learned from Socrates construction and operation, and then we will have innovation management and Socrates dissemination, Socrates business plan and exploitation strategy, and finally a short round table in a conversation about the technology future and what we have learned with this project. So we take 10 minutes, we start in 20 past 11. Sure. I don't know, Luismi, if you already have the presentation. If you want,
yes,
you can already.
Yes, I'm going to try to share my screen.
Okay, perfect. Thank you, Luis.
Okay.
And you are going to share with Tom, or you are going to make the whole presentation?
No, I'm going to share with Tom the presentation.
So Tom will have to share.
No, I'm going to present. Well, can you see now all my full screen?
Yes. No, but we see
the wrong screen.
Yeah, we see two screens. We see the two screens at the same time.
You have to switch off the screen because we see like your notes and the next slide instead the main screen.
Now?
We can't see anything. You stopped sharing.
Yeah.
Excuse me. Excuse me. No, I suppose.
Yes, now.
Yeah,
perfect. Thank you, Luismi.
Okay.
1 minute.
Yeah.
1 minute and we start. Let's wait until it's 11:30. Yes, because. Okay, in 1 minute we start.
Okay, yes, Ricardo, to everyone knows we have like a 20 minutes of delay, but I think that is not so bad for a webinar.
Yeah, it could be worse, but
yeah.
But I'm sure we have room for comments.
Porque le entró el tema de la marcha en el cerebro. Sí, que tiene un problema. Este es el que está malo, ¿no? Sí, exacto.
So someone is getting.
Don't worry, when I check this
yeah.
kind of problem, I can mute people that are open microphone.
Okay. Well, then we start the second part of the info day. Now the first presentation is scaling up and Socrates technologies opportunities that will be presented by Luis Romeo, professor from the University of Zaragoza, and Thomas Hill, research engineer at CaL-CSP Europe Limited. So, when you want, Luis, Tom, the floor is yours.
Okay, thank you very much, Ricardo. Good morning, everybody. We are going to present some ideas about the scaling up and future opportunities for the technology based on the Socrates results. Today we are, currently we are finishing the operational period and we are analyzing the data that we are obtaining in the last test. So this is not the final conclusion. This is just we want to share with you some general conclusion that we have learned in this period with the experience and the knowledge that all the partners has get with the Socrates project. The idea of this work is to try to reduce the risk for future advance of the technology readiness level. But and this is because, as you probably know, the scale-up is always a challenge, because sometimes small installations are sometimes more difficult to operate than bigger ones. For these reasons, we have developed a two-step scale-up until we reach a commercial installation based on calcium looping in CSP technology. The first step is to develop that we call Socrates Alpha, that is to go to tier L5 to tier L7 with the idea of increase the size by 30 or 50 30 or 50 to reach a power of 300 until 500 kilowatts. With this idea, we know that we will need more openings for receive all the energy from the sun, and we are going to increase the cross-sectional area of the calciner to introduce the energy from around 900 square meters of heliostat. In this step, we assume that we can use a Brighton cycle with CO2, as Umberto has mentioned before, and we are currently analyzing the type of the cavity, where the idea is to not in this scale not to reduce the cost, but reduce to know the feasibility, the technical feasibility of the concept. And then when we have this step solved, the next step, that is a commercial one, we assume that we are going to, with this step, we will reduce more the uncertainties in the design. The last step will be to go one order of magnitude bigger, and then to reach a full integration of CSP with calcium looping. This is more or less the technology development for the future for the technology, and now we are going to analyze or to give general ideas about how it's the performance and how we see the critical variables for different equipment. Regarding the solar field and receiver that are the main responsible of calcinations, Ricardo has previously shown some good calcination figures in our installations. Here is critical the temperature. It has to be really high, around 930 degrees. But we know that as has been also commented previously, that we can reduce these temperatures using steam or helium to reduce these high temperatures and to achieve less critical these temperatures. Regarding the receiver, we know that we have to increase the number of the pipes to receive all this energy, and the heat transfer is going to influence strongly in the maximum diameter of these pipes, and the number of pipes will be depending on the selected size that we choose for the scallop. Regarding the power block, as Eusha has previously mentioned, we have used stirling, and has been important for the project, because it's a way we can demonstrate that we are able to provide electricity with concentrated solar power. But we clearly know that, as also Umberto has said before, we need another concepts to achieve a high efficiency. We can have obtain efficiencies up to 45% with CO2 Brighton cycles, but also with this efficiency will be higher than actual efficiency using more commercial cycles as ranking. This power block, it's one of the challenge when we to go to bigger size. We have to change this concept. It's not really, I mean, a very challenge because it could be a commercial installation and give us the opportunity to improve the whole concept because we obtain higher efficiencies. But it's relevant when we have to change to other scale. Regarding the Carbonator, as Kyriakos has previously mentioned, we have seen that the entrained flow reaction has worked without any problem in the project. For the next scale up that we call Socrates Alpha, it is reasonable to maintain the design. But if we want to go to a bigger scale, we know that we have to change to fluidized bed reactor, and that is the idea that we have when we think about that we call Socrates Gamma. This is the commercial step of the Socrates. We have seen that the residence time of the particles is a very critical variable that influence the carbonation conversion and then influence the whole installations. Now we are currently preheating carbon dioxide, but in the future we see that we have to also preheat solid particles in order to achieve a good carbonation conversion, that it gives us the energy to be recovered in the power cycle. So this is a very critical variable, but in this small size it has been controlled and there is no problem. Another variable that influences a lot is the heat transfer. We need to design reactor with homogeneous heat transfer along the reactor to avoid any big thermal gradients that could influence the main reactions. And finally, we also need a low level of attraction and agglomeration of particles, and we have not seen any problem related with this part. And regarding solid storage and conveying, we have solved any problems, operational problems that we have faced in the project. We have developed some operational strategies and some ideas to avoid any problem with the solid circulation. That is really relevant because we are this is also critical for the project. But with mixing with silica, with a small fraction of silica, we have avoided any problems. And here the two main variables that we need to face, it's the capacity, that it's mainly dictated by the expected dispatchability of the plant, how much energy we want to storage, and then the discharge rate, that it's influenced the power that we are able to recover from the storage. Again, it is important to have low attractions and to consider some safety and environmental issues, but no problems has been related in the operational of the plant. Then this is the calciner, and Thomas, the floor is yours to to comment this part.
Thank you, Luis. So it's very nice to be here, and hello everyone. So in terms of the calciner, I think one of the big recommendations is that it needs to have sufficient scale. So with the design that we have, it requires, the residence time is dependent on the scale of the unit, and therefore future units, if you can make them bigger, and as we've seen, that's the plan, you should be able to get a higher residence time and more efficient heat transfer. So that's really important for the calciner. Another important thing, which again comes with scale, I think, is increased solar efficiency. So we've got the theoretical or the design aspects there to help increase the fraction that's usefully absorbed. But again, with increasing sizes of solar fields and solar receivers, you can get higher concentration ratios, and that helps. It also helps to improve the homogeneity of the energy distribution. I think we've talked a little bit about the solvent properties, and sorry, this should not say Socrates Alpha, since that's not the current project. It should just be Socrates. It found that performance for the calciner did depend on the particle size distributions and the composition of those sorbents. As Luis was saying, it's important to get the solvent properties right for the calciner, the carbonator, and also for the storage. If we're going to store this material for days or weeks or months, we really do need to make sure that it stays in a suitable state for use in the future. Great. Could I have the next slide, please? On the subject of calcination, I wanted to touch on some other industries where the advances made in Socrates could have an impact. So calcination of limestone, but also other minerals, is a large energy consumer around the world. So for example, the cement industry emits around about 7% of our CO2 globally. About 4 to 5% of that is processed CO2, but the other 2 to 3% comes from the fuel. So 2 to 3% of all CO2 generated comes from heating up cement plants, essentially. So that's a huge market for energy, especially when you consider that the traditional fuels for cement plants are coal and petroleum coke. Nowadays, there's been a move towards alternative fuels, such as refuse-derived fuel, which is essentially a fraction of what comes out of your waste at home. But if this was able to, but that contains fossil fuel in the form of perhaps textiles or plastics. So that is fossil CO2 that's entering the atmosphere. There are other industries as well. So there's lime here, metakaolin, which is sort of a calcined clay. Phosphate, some of that requires calcination. Magnesius, that's magnesium carbonate rather than calcium carbonate. Note that this is a log scale, logarithmic scale on the y-axis. So you can see here that, for example, the lime industry is 10 times the size of the metakaolin industry. What we also have are the little red and yellow dots, and those represent roughly the temperature you need to achieve in those processes. And then on the right we have the concentrated solar power gross thermal output, or what I found as estimates for it, and also typical temperatures for CSP. As you can see, CSP gross thermal output as it stands is larger than 3 of those industries, but not as large as lime, and certainly not as large as cement. So if we were to be able to apply CSP to these industries, it would be a really big opportunity for CSP companies and organizations worldwide. Of course, one of the big challenges is to get that temperature up, and Socrates is aiming to do that, and I know other projects are as well. And so I think that shows that although it's a big challenge to do that, and there's a lot of progress that's been made, but also progress to be made. The returns for the CSP industry in general could be, very, very large indeed. And with that, I think that's the end of the presentation. Thank you very much.
Okay, thank you very much. Thank you very much, Tom. Thank you very much, Luis. Following the same strategy than before, we pass to the next presentation and we collect all the questions at the end of this part. So the next presentation is lessons learned from Socrates construction and operation, that it will be shared by Juan Valverde from Virtual Mechanics and Carlos Ortiz from the University of Seville and University of Loyola.
Hello, can you guys see the presentation?
Yeah, perfectly, Juan.
Cool. So we are going to talk a little bit about the lessons learned both from the construction. We'll be talking about the construction, and afterwards I'll pass to Carlos Ortiz to talk about the operation. Most of the construction was already finished when we had the meeting in June. So most of the pictures and all that are repeated, but I will try to talk new things about the construction. And then Carlos is going to provide some interesting information about the operation, which I think is the most interesting part of this talk today. So a little bit of agenda, but we will be talking about the solar field, the solar calciner, the integration of the different systems, the construction that we have performed, and then a little bit about the control. And then, as I said, the operation and testing, which will be provided by Carlos. So for the solar field, it is interesting to say that we had many constraints for the design, like low space, low money, as always. We had to have a vertical beam down system, so it was difficult to get this, but we were able to design something that was able to work, okay? And eventually we managed to put the energy inside the indirect calciner, okay? So we were putting as much radiation as possible inside the calcination reactor in this cavity here. And for that, we had to do many ray tracing simulations. At the end of the day, we were able to qualify the system of design conditions, and also to build a secondary reflector that was open to be fine-tuned during the operation in order to, let's say, accommodate different conditions, okay? You can see here some of the details of the mechanical design of the secondary reflector. Also, we had to build the tower unmountable because the project should be taken to another location in the future. And most importantly, construction was okay, and the objectives were more or less done, okay? From the side of the cavity receiver, we had to deal with very high temperatures, so it was very important to select suitable materials for these high temperatures. And the big issue here was how to have let's say a radiation map onto the cavity receiver that is as homogeneous as possible. So for that we have done different tests and considering the material in an oxidized state, non-oxidized, painted with radiation pyromark painting, etc. And eventually, in order to be able to integrate all the equipment coming from Greece, from our partners from Calix, also from TTC Germany. So we had many different systems to integrate, and it was essential to have a proper three-dimensional BIM model in order to integrate everything. So the construction was soft in some way, and not many problems were found in the integration, other than sometimes we could find differences in the aid or something like that that we had to fix, but nothing too important. Another interesting thing that we had to do was the storage system for the particles and the CO2. We use an open modelica model to size the storage tank and the control system. And this is something that is working very well, and the scale up is very easy. So we are very happy with this part. And from the instrumentation and control side, we were able to take all the measurements from the instruments and be able to control the system properly with the help of our partners from EasyTech. And then I'm putting this picture here because we had to move many times the heliostats and move and fine-tune the secondary reflector in order to improve the radiation onto the receiver. And another interesting thing that is not the focus of the project, but at the end of the day is very, very critical, is how do you move the granular material around the plant. And that was very complex at the end of the day, because some of the equipment was very critical and sensitive to the operation conditions, and also the high temperature piping, because we are moving very high temperature fluids. So we had to deal with this complex design. Other than that, everything ran very smooth, and I would like to leave some room for Carlos to talk about the operation. So very shortly, some quick lesson learned from the solar field design. The lesson learned is that the low-cost technology is difficult to control. So I mean, when we have a scale up, we won't be having this problem. The secondary reflector performance is difficult to quantify, and this is also real in real beam down systems in the CSP industry. And we think that for the scale up, which was shown before by Luis and Tom, we won't be using the beam down technology, so everything is going to be easier. From the point of view of the cavity of the solar calciner, is really important to understand the performance of the different materials, and we are going to have a very high temperature, so that the materials are going to oxidize and things like that, and we need to characterize the materials in these conditions. For the system integration, it's important to take into consideration that the high temperature piping is expensive and complex, and the particles moving is a big challenge. So it has to be taken into consideration at the beginning of any further project or parallel project like this. Construction, shouldn't be a problem from now on, and because you have to integrate many different and different nature of equipment, but one is done, it can be replicated easily. And for the solar field, you have to be ready to fine tune and do changes on the system. So it has to be a a system that can be changed like we did with the secondary reflector. And from the storage point of view, everything is all good, so no further comments. And now I will pass to Carlos to talk about the operation and testing. Go ahead, Carlos, when you like.
Okay, thank you, Juan. Hello, everyone. This is Carlos Ortiz from Loyola University. Please let me share with you some of the results that we are achieving during the test campaign that we are developed within the project. We have developed more than 100 tests from May when we characterize the main equipment of the plant to November, when we are carrying out multicyclic calcination carbonation test. Typical test consists of evaluate the temperature and the heat flux patterns within the reactors, evaluate the flowability of the material, potential aggregation, material performance at the end of the day, and later on evaluate at lab scale the reactions extents to gain knowledge about how the reaction is occurring. Juan, could you move the presentation? Thank you. Regarding carbonation, it's important to note the significant improvement that we are achieving thanks to the knowledge gained within the operation. Now we are obtaining large reaction extents up to 77% when we are operating the carbonation reactor at 800 Celsius degrees. And thus we are demonstrating for the first time at kilowatt scale with kilograms of materials that carbonation reactions can occur in several seconds, just in several seconds, which is a main outcome of this project. Please, Juan. The same for the calcination. We have developed a lot of experiments for calcination reactions with several calcium oxide precursors, such as limestone or dolomite, for several reaction conditions, temperature, pressure, for different particle size of the materials. And we are observing that and demonstrating that we are obtaining calcination of fine particles just in some seconds. We are observing also that the best performance for the reaction, the best reaction extents, occurs for particle size around 70 microns, instead of lower side particles, which are more difficult to manage. Please, next slide, Juan. Thank you. One of the main results of the project is the experience that we are gaining in multicyclic calcination carbonation test. As said before, this is an important novelty because it's the first time that this occurs at kilowatt scale. In this slide, we can see the results that we are obtaining at lab scale after the planned operation. Reaction occurs at prototype scale, and we send the samples to the CSIC lab, when our colleagues from the CSIC analyze the reaction extents from XD or from thermogravimetric techniques. So we can see and we can comprobate that reactions occur as expected. Most of the time, the reaction does not occur completely. So partial calcination and partial carbonation we are obtaining. But in any case, we are demonstrating that it's possible to develop this process for thermochemical energy storage. And next slide, Juan. Thank you. And finally, we can see here an estimation of the materials behavior obtained after the plant operation at the lab scale evaluation of the reactions stems. We can see how the materials are converting from calcination, from calcium carbonate to calcium oxide after each step. So we are demonstrating that thermochemical energy storage occurs. One of the main issues that we are achieving, as said before, Juan and also Luis Miguel and Tom in the Scalling is about the materials handling, because it's not easy to move fine particles of just some microns around the plant. So we are experiencing some problems with blockage or material losses, but this is the information that we are gaining for the operation, and we are demonstrating effectively that thermochemical energy storage occurs within the SOCRACES project. And this is all for my side. If you have any question, please let me know.
Carlos, I will add that regarding the last comment of the handling of the particles, that we found out also, which is interesting, that moving small particles is difficult, but if you move low quantities of small particles, is even more difficult, because the piping, the tubing, everything is really small, because the flows are really small in the scale that we are moving, that eventually it was even more difficult at this scale than at a higher scale, more flows or higher flows. So we were facing even these difficulties that are only for the scale, the small scale that we are doing. Probably for higher scale, we won't be having as much problems on the particle handling.
It's important to add to this comment that we are achieving to move these particles with a huge success, because we are able to move these particles along the reactor with conveying management. So this is one of the main results also for the SOCRACES project.
Okay, thank you, Juan. Thank you, Carlos. We can leave some discussion for later on, if you agree, and we move to the next two presentations. We have a roundtable later, and we can we will give floor to the questions for sure, and we can express what we have learned, because it's important that now everything is working, but at the beginning it was hard. It was not. It has been really hard.
That was my point.
Even the construction. Even the construction, Juan has said everything has been smooth, and okay, well, we have a pandemic, we have no providers, so this has been really. So the next presentation is the innovation management and SOCRACES dissemination, that will be presented by Mrs. Ángela Magno from Bioazul. So Ángela, when you want, the floor is yours.
Yeah, thank you, Ricardo. Good morning, everyone, or good afternoon. Here is my presentation. Well, now, as you can see during all this morning, we have a lot of innovation to manage here in SOCRACES, and I'm going to talk a little bit about it, how we manage this innovation. Well, I'm Ángela Magno from Bioazul. We are engineering and technology and consultancy, and here in SOCRACES, we were in charge of administrative management of the project, and mainly innovation, IP issues, exploitation management, and finally the dissemination exploitation. So Let's start about the innovation management of the project. What do we want to do for manage the innovation arising in our project? Well, innovation are one of the main factors driving the growth and economic competitiveness of companies and industries. So our idea was trying to have decision-making mechanisms to select new ideas, new innovation for further development of the technology. The aim was to define which innovation can become really key exploitable result with real market potential for our consortium and for other companies that can collaborate with us. And how we evaluate this innovation? Our idea was create a multi-criteria matrix for make a qualitative evaluation. We define at the beginning 3 steps for do it. Step 1, the criteria selection. Step 2, selection of the innovation. And finally, step 3, score those innovation. When we start this work, we detail these 3 steps, and I'm going to explain in detail each of the steps that we follow. Within the step 1, the criteria selection, we define this multi-matrix structure with 3 different criteria: technological, economic, and environmental. At the beginning, we established some indicator that could be interesting to study, although this indicator will revise in a further step in our work. So after that, we go for the step 2. I think this is the more important part of our work, the selection of innovation. At the very beginning of the project, we established like a previous idea of how many key explorable results we will have. And according to the partner, we think that we can develop 22 key exploitable results. This was in one of our first deliverables. After a first year of technical work, but previous of the prototype construction, we identified 28 innovations that we start to work and evaluate. At the final stage of the project, after the prototype design, we developed and evaluated 30 innovations. Also, I want to explain that during the exploitable strategy seminar that we were lucky to have this experience, this service with the Horizon Result Buster provided by the European Commission expert, we evaluate and analyze 3 of these key exploitable results as our main result of the project. Also, to be able to manage this innovation are the most important. To evaluate this innovation, we group the innovation according their identity, their nature. I group by work package and different kind of innovation. So we make these different groups. Regarding the carbonation, we establish models, equipment, and studies. Also, we made the same for solar calcination. In the case of the power system, we talk about integration innovation or innovation related to the integration of the power system, the Carbonator, and the stirling. And finally, for the system integration and control, and for the validation and test, we manage all these innovation related this in only one group. But in this moment of the work, it was very important to have a revision of the indicators because it's necessary that these indicators were suitable for each of the innovation, for each of the group of innovation that we established, because the aim was that each group of innovation has been scored with the most suitable indicator to know at the end which innovation will be promising and will be exploitable at the future. Here you can see more or less how we work with the indicator and the groups that I mentioned before. For example, related to the work package 2, here you have the specific model, the equipment, the studies, and the first here the first table was the initial area, the initial indicator that we established, novelty, implementation cost, ease of implementation. But when we start with the work, the partner revised according to the nature of each group. For example, for equipment, we talk about the dimension, we talk about the response to operational condition, also for the sensitiveness to change in operation condition. Meanwhile, for the studies, well, different indicator. We talk again for ease of implementation, but for example, we don't talk about the dimension of the carbonator because it's something that is not applied to studies. We arrive to step 3, score this innovation. But to be able to score the innovation, we need reference, we need benchmarking. So we ask for the consortium if are the innovation being developed comparable to what is able in the market? There are at the state of the art that could be a reference for us, or have the one of the partner of some of the partner done this comparison already for the development of a published paper, a scientific paper. So finally, the idea is that we set reference for each group and we score also the reference according to a qualitative idea, high, medium, low. Here in this table, you can see better what I refer. Once we have the indicators, we need a reference data, and we make this reference data with the according reference in another system available, or in the publishable material that already was in the market. So we established that, for example, for the study related to the Carbonator, regarding the effectiveness, it was marked as medium. Regarding the novelty, is also medium. This was our reference data that allow us to score finally our innovations. So here is the idea, the main result of our work in the innovation management. We try to score qualitative, high, medium, and low, including explanation, and we made this work twice. Once previous to the prototype, and after the prototype construction and the operation, with the result that Juan and Carlos explained us. This process allows us to compare the initial assumptions that the consortium have in mind according to the studies, according to the design, and after, once that we have the final results, we was be able to know if we are wrong or if finally we will be lucky and we achieve our goals. So the evaluation had led us to identify which solutions are more competitive and promising for the future, for next development, further development, or even for arrive to the market. Here is just an example of our big table that we developed with, you can see at the top of the table, there are the code for each of our innovation. The gray column is the benchmark for each of these groups that I show you. And this also is easy to understand how is the code. Green is the higher score. Yellow, orange is the medium, and purple is low. So it's not bad for this table, but we made a really nice work with this score. Well, we are happy with the result. So now we are trying to do it to finalize all this work. We also want to score the innovation according to the criteria established at the beginning, environmental, economic, and also include the criteria of social, the quality. I think that is important to take in reference for the different technological development that is made. We'll evaluate this criteria according to the output that we have in another important task of our project, the life cycle assessment, the life cycle cost, and the business plan. And also, we are right now completing the questionnaire developed by the DG Connect Innovation that allow us to have like a further result, further comment in the innovation, in the status that the innovation are now after the test and the operational or the operational work that was made in the prototype. After that, all this innovation management, all the projects of the result that we obtain, also we take care about the dissemination and the combination and communication of this work. And I'm going to pass very quickly, just like an overview of the main activity that we developed during the project. We have a website. I invite you to visit our website. It's launched from the beginning of the project and is www.socrates.eu. We have a news section where you can find different news related to the sector, the CSP sector, the energy solar sector, and also the different events that the partner or the consortium has done during the project. Also, we develop material to disseminate specific about the project. The leaflet is general information about our work, and also we develop a technical brochure mainly focused in the stakeholders, in people that will be interested in work with us on in a future development of the technology. We also have been active in social media. We have our LinkedIn profile. Again, please visit and follow us. We have now 156 followers, and a YouTube channel where we have created different playlists. One is Socrates team. It's very interesting, where you can find a short video from each of the partners that compose the consortia, to understand who we are and what is the work that we develop within Socrates, and also different short video about the plant, the construction, and of course the full video that Ricardo shows at the beginning of the webinar. And I want to just review a little bit this event that we organize as Socrates. Pandemic is something that was crazy for us, because we have a lot of delay in the construction. We not be able to see each other face to face since 2029. But also we take the opportunity that the pandemic gives to us to organize more webinars that we have thought at the beginning. So we have our Socrates webinar on June, where we talk just about our designs, our work, and the presumption that we have regarding the prototype operation. We also organized in June a joint webinar together to another CSP project, because we also have the opportunity to receive the service from the booster, where we create like a group project with Mustec, Next Tower, Sphere 3, and a couple more of a project. And then we have the opportunity to be able to create synergies, and also to create a R&D portfolio of all our projects. In October, in the framework of the Sustainable European Energy Week, we organized together with CSP Euronet another webinar where we talk and we discuss about the challenge that the CSP is facing now and in the following years. And also we have the opportunity to know better the funding opportunities that are open now and in the next year for projects, further development, and new proposal for us. So it's also in our YouTube channel. I invite you to go and see, because it was very, very interesting. And finally, today we are in our final info day. We have a lot of scientific publication during the project. This is just a summary with some numbers, some figures are not updated. I think I need to update, but we are very happy because we think that we have a very nice and good results during all of our work that can provide us the opportunity to make different papers. And finally, we are open for networking, for continuing to exploring synergy with another project. We develop several newsletters together with this group of CSP project. And also we have invited through third to be part in this ecosystem stories. We are very happy because we think that CSP are very promising for us for continuing further development and further opportunities for Socrates technology. So thank you very much for all of you. If someone at the end have any kind of question, I'm here.
Okay, thank you very much, Ángela. So we follow the same structure. We condensate all the questions at the end of the second block, and the next presentation within the agenda is Socrates business plan and exploitation strategy that is going to be presented by Denisa Mateus from SPI. So, Denisa, the floor is yours.
Thank you, Ricardo. So my name is Denisa Mateus. I work at SPI. We are a consulting company, and just let me share. We are a consulting company, and we have a strong expertise in business plan and exploitation plans elaboration. Are you seeing my screen?
Yes, perfectly.
Yes. Okay. Thanks. So regarding Socrates technology, this technology could give an important contribution for three main market sectors, namely the power companies, the electricity grid operators, and the cement industries. So why these customers should implement this technology? We identified several value propositions for these segments, and just to highlight, for example, for power companies and electricity grid operators, the main advantage is the high energy storage capacity and the low cost storage, and it could contribute to decrease the electricity price. For example, the cement industries, as Tom already presented before, this technology could give a contribution, an important contribution for circular economy and for the reduction of the energy consumed by these industries. So for a potential client, it's important to know in advance the costs of the technology and the profits or revenues that could be obtained with its implementation. So based on the work developed by our partners from TTZ that elaborated the life cycle costs analysis, it was assessed a total cost of 152 million euros, for which include the planning, construction, and operation of a CSP technology. And importantly is that this could give a significant contribution to decrease the levelized cost of the energy to 88 euros per megawatt hour. So based on the LCC analysis and with the aim to enable future investors to have a perception of the return rate, we developed a dynamic tool to simulate the main financial feasibility indicators, such as the internal rate of return, that is the financial metric to assess the attractiveness of an investment, and the net present value used to analyze the profitability of this project. So this tool has several includes the analysis of several factors such as time horizon, the investment costs, the installation costs, operation and maintenance costs, for example, the price of energy and the energy that could be produced. So just for you to have an idea of the tool. So this is this is an Excel file, but where we can introduce all the preconditions to be assessed. For example, regarding sales and services, prices associated, the definition of the energy costs, even expenses with personnel, the capital of investment. So a lot of factors could be included, and at the end, we can estimate the main financial indicators. So the economic indicators, as you can see here, for example, the liquidity, the business risk, and at the end we have the NPV, the net present value, and the internal rate return estimation. Oops, sorry. So depending on the information provided by the customers, this tool enables to estimate the profits and assess how these factors could influence the return rate. So our aim was to develop a tool that could help to understand where we could improve or which factors that we could change to turn the technology viable financially. So, for example, for a hypothetical scenario where we assume initial investment of 100 million euros, industrial capacity of 100 megawatts for a period of 10 years and with a construction phase of 2 years, and assuming the 120 euros of energy price, much lower than the real one estimated, we can have an internal rate of return of almost 7% and 7 million euros of net present value without the initial investments. Although these estimations cannot be, there are some problems that cannot be considered at long time. For example, large fluctuations in commodity prices, costs, or changes in the price of engineering and manufacturing, oscillations in the fuel price, and the effect of carbon policies that could affect competitiveness of the investment. So just to conclude, SOCRATCES technology could take advantage of several market opportunities, namely establish CSP industries, mainly in Spain as a global leader, because there are plans to enhance the capacity of the Spanish CSPs with retrofitting systems. Also the United States, that it's the second leader. Moreover, new CSP projects, mainly in China, that is developing during the last year, were under construction several CSP plants, also the United Arab Emirates, Chile, and India. Moreover, emergent economies that have plans for future CSP projects, such as Morocco, Zambia, and Botswana. So I'd like to thank you all for your attention.
Okay, thank you very much. Well, with this presentation, we finished the second round of presentations, and now a round table in which it will be relatively short, in which partners of the SOCRACES consortium will answer two specific questions. The first one, after SOCRACES project, how do they foresee the status of the technology and the next steps? And the second question is related to which are the strong points they have identified and they have gained with the project, and which are the open issues that still remains and must be reinforced in their specific activities. But before going to this round table, start to answer these parts by the participants on the round table, I open the floor to questions if you have any related to the previous presentations. Is there any questions? If don't, we can make the questions after the round table. I will open also the floor to any doubt, to any. I don't see any questions, so we pass to the round table. And at the same time, there will be issues that are open, that they will appear for sure. So in the round table, we will have Professor Vittorio Verda from the Politecnico di Torino, Dr. Spiros Boutetakis from CERT, Center of Research of Hellas, Professor Luis Pérez Maqueda from the CSIC, Professor Luis Romeo from the University of Zaragoza, Professor Angeliki Leminodou from Aristotle's University, and Dr. Juan Valverde from Virtual Mechanics. So, first of all, thank you very much, all of you, not only because being here, but also for this really nice and challenging travel that we have, journey that we have made along these years. And I put again, and Dr. Choris also from the TTZ Bremerhaven. Thank you, all of you, because of your contribution along this project. And I put two questions on the table, and please answer in the ways you consider. First, I will. The first one is, which are the main benefits, knowledge, advances that you have identified related to SOCRACES project, related to this, which are the open issues that you still identify, if it maybe if there are some future projects or advances, they should be. The first one, main outcomes regarding your activity that you have identified along SOCRACES project. And the second question can be mixed in your answers. What's next? What after SOCRACES? How do you see the future, and what do you think about potential evolution? So, in order to give room in different orders, so maybe some volunteer to ask the first, to answer the first, if don't. Okay, so I don't know, Vittorio, if you would like to share with us your point.
Okay, thank you very much, and thank you for inviting me to this roundtable. First of all, I'd like to say everybody that it has been a real pleasure to work in this project. It was very ambitious, in my opinion, and also the consortium was very good, very nice, very well prepared. The people participating, and also nice as people. So meetings have been also very pleasant. Concerning the question you made, I don't know if you want a general reply or very specific to the activity we have performed. I've understood.
So, fully open. Feel free to. We are several.
Okay.
We can give I think that at the end we will give among all of us. We will give a global. So feel free.
Okay. Well, I think there are people most suitable to reply to reply in a general way to the general advances of the project, and also the open questions related to the project. So I'd be a little bit more focused on several advances and possible future works from our perspective. We have worked on basically on the integration of the cycle to different power cycles. In my opinion, the advances we were able to make, even if not fully exploited, are related with the integration of heat recovery systems that should operate in transient conditions as a storage unit does, which is not an easy task from the modeling viewpoint, from the mathematical representation viewpoint. It's something that we started considering several years ago, and still it's something that we are under development. And thanks to the SOCRACES project, we were able to make some advances in this regard. Concerning possible future applications, in my opinion, we may orient the storage technology towards different applications, different than the solar applications, particularly, in my opinion, in the case of industrial systems. There are many possible opportunities characterized by different temperature levels, for instance, different operational constraints. And in my opinion, the technology that has been developed under SOCRACES can be very useful to this type of applications.
Following the two questions, maybe Angeliki, would you like to add or to give us your opinion about the future of the technology and how, for instance, the new models contributes to it? You're mute, sorry, Angeliki, you're mute. We don't hear you.
Okay, can you hear me now?
Yes, perfectly.
Yes. First of all, I would like to thank you for inviting us to be member of this consortium. It has been a long time ago, more than 4 years, almost 5 years ago, when we first, you contacted my student, and then a very fruitful collaboration started. It was a real pleasure working for almost 4 years. Our aim was mostly to develop kinetic models. And even though this calcium looping, which consists from 2 rather simple reactions, we found actually that in the literature was full of many empirical models, which were questionable concerning their validity. So we tried very hard with Thanasis and Andy to work a bit on the mechanism of the reaction, on trying to develop more robust models and models for calcination and carbonation that can provide reliable data that can be used with safety, I would say, for a proper design of both the calciner and the carbonator. And I think that we succeeded. not 100%. Of course, there is always something better, something more clear, more robust model, but still we have advanced a lot the knowledge, our knowledge, and the knowledge to our scientific and technical community on how to develop models and how to validate them. So I think that we were very lucky working for all these years, and we are looking forward to the next projects, in which we would like very much to further contribute with our expertise in kinetic modeling, and not only. Thank you, Ricardo, and thank you all the partners.
Okay, thank you very much, Angelique. Yes, it has been a very long journey. I fully agree. It's but nice. It's important. Now we are finishing. Well, there have been a lot of stages, like in all the projects. Yeah, it's in this period we have had the beginning of the concept, then the design, then the prototypes, the components design and start construction, then the pandemic, then direction of the pilot, then so. But it's really nice project at the end. To follow with the opinions, I'm following criteria regarding the different work packages, more or less. So, I don't know, Gerhard, if you would like to give us your opinion about the outcomes that we have obtained and about the future.
Yeah, so thank you very much, Ricardo. And yeah, also for us as TTZ, it was quite an exciting project. And of course, we had many technical challenges, but I think we had a quite good team in the project with all those partners involved. And so we were really able to deal with all these challenges occurring in the project. I think these kind of projects, and there's also this technology, I think will have a high relevance in the future. I don't know if you are aware of it, but in Germany we are now getting a new government setting new climate goals. Of course, the SOCRATES technology itself is not so much relevant for Germany because solar irradiation is not good enough. But we cannot think country-wise anymore. We have to think globally, and also referring to the Glasgow conference, I think it's a duty we all have in the future to work on improvements of our energy footprint, avoiding fossil fuels wherever possible. And this kind of technology is a good contribution because it allows decoupling of, let's say, solar irradiation and availability of electricity in a different way and in a way that is quite interesting. So I see, especially for countries, and this was also in the last presentation, very obvious where are activities ongoing. And I think these kind of concepts need to be further developed, that we really reach a technological readiness level, that these technologies can be implemented. And therefore, I think it is important to bring it to a next step. We have seen in our work that the scale and the scale up or scale down can be critical for the overall performance. And I think putting this to the next level of technological readiness and also putting it to a larger scale would be the most important step in order to have a successful implementation.
Okay, thank you very much. Thank you. I fully agree that we can contribute with this technology. I would like to add, if I may, that of course our technology is complex. It's complex in the design. It's complex in the concept of the parting concept. But one benefit that is implicit in all the previous presentation and in the discussion that we have had before. But once the designs are done, once the concept is developed, the construction by itself of Socrates technology, as we have conceived it, the different partners, so they are pipes that can be made in relatively simple metal workshops. They don't need a spatial, a very state-of-art industry for constructing it. And this is also an opportunity for development of new business in not so high technological regions or things like that. So I think something that is implicit within the presentation we have seen that is something that is important to highlight.
This is very important, Ricardo. If sorry for interrupting you,
no, please. It's an open. It's open. I think it's better if we interrupt us and we talk. So please.
Thank you. So just to say that this is really important because at the end of the day, you know that at the
I don't hear you, Juan. It has been. No,
I'm not giving.
Yes. Now okay.
Now? Oh, sorry. So sorry, Ricardo. Just to say that this is really important from the industry perspective. You know that we work we have a lot of activity on the CSP and energy storage industry, and we go to the plants and we work close with the operation and managers and even the owners of the plants, and even the only cost-effective storage system, which is actually the thermal energy storage based on molten salts, on the two-tank molten salt technology, which is, I mean, I can't think of anything less complex than that. Okay, it's just two big tanks full of salts, one with hot salts and the other with cold salts, and then you are transferring the energy to another fluid. You know, it's really easy and not complex at all. But at the end of the day, when you are in the real life, you find the complexity in other things, you know, in the operation, in fails that happen and things like that. So having a very low level of complexity for the equipment to build is very important, because at the end of the day, you are going to find it in the real life. So if you have the drawback of building something which is quite complex, this is going to penalize you at the end of the day in the real life.
Sure, and following this comment, also it's also once that is developed, that is challenging. That so it's also cheap, relatively cheap to construct or for the scale up. So that is also something
it's super important, because otherwise nobody's gonna do it. You know. Yeah. This is the real thing, that it must be cost effective and safe.
Absolutely. And how do you see, like following with Luis Perez, for instance, if you don't mind, how do you see, you have identified amazing improvements related to the effect of different additives or working in different ambients related to the calcination. For instance, today you have presented calcinations and 680 Celsius degrees. Yes. So this is a wonderful temperature. How do you see this for application at the technology, at the future, or because I think it's, what is your vision about?
Okay. So first of all, I will join also all the people here in the panel. It was a pleasure working with all of you. So we have a very complex project with many challenges. So we have all of us to work very hard to solve them, because as I said, you, Ricardo, we have not one project, but 3 or 4 at the same time running all together. So regarding calcination, yes, there is still a place for improvement. No, for example, of course, in the SOCRACES plant, the one we have constructed so far, the experiment has been done just under conventional conditions, no? But Of course, we could add, for example, steam to the system. We could decrease the temperature of calcination, so we could get higher degree of calcination, even at lower temperatures. And also what we observe in our studies is that the cyclability also increases. So the performance of the calcium oxide we obtain from this calcination under steam conditions will be more active for carbonation. So it will be faster the process, and also the extent of reaction will be larger even after a significant number of cycles. So this is something that we might think for future activities, no? Because I think we still have room for improvement and for developing this technology.
Sure, absolutely. And for instance, to add also the contribution of Luis Romeo, how do you see? You have presented previously about future applications, but what's next? What's next after the experience that we have gained?
Yeah, first of all, I would like to first to thank as the rest of the partners for the nice project and nice project management that you have done. And I think that the first message that I want to share with you, it's you ask us about what we have learned about Socrates. I think that it's important to highlight that to say that we have learned that the process is possible, that we have demonstrated at a relevant scale that the integration of calcium looping and concentrated solar power works, and of course we can improve all of this equipment, but we have achieved a good carbonation figures. We have achieved also a good calcination. We have achieved a proper integration with a power block, and everything run smoothly. So it's I think this is the first message that we have to highlight in the consortium, that we have done a good work. And so it's really nice to be involved in a project that is successful. So it's really nice. What about the future? Well, we have also performed a lot of studies for the future. We have a lot of knowledge, and we have developed new ideas. And I think that as I mentioned before, that we have to go to a bigger scale. I mean, some concept when we go to demonstrate this concept in an industrial or commercial site, some concepts of the technology change, as for example, to change from the entrained flow to fluidized flow, to change the type of power block to take advantage of all the heat that we have. So we are going to face another challenge, another problems, but I think that it's we have to do it if we want to see this technology in the future. And also it's important to increase the industrial interest in this kind of processes. We need some industrial leader that takes the leader, and we go with the whole industry to solve all the problems and challenges that we have to do in the future and in the scale up. So I think that it's the both things. That's the both message that I want to share with you. The first one is the process is possible, and I think that we are all really happy. And the second one, that we go further for a scale up of the technology.
Okay, thank you very much. So I don't know if Paris, if you are connected. Paris? No, I don't see him.
No, I think that he has problem and he.
Okay. So for Juan, Juan, one question for you. You have said we have a smooth construction and a smooth operation. So it's well.
We are running a company, Ricardo, so we have to lie.
No, it's not lie. So it's important to have, well, when we were going to start the construction, first pandemic wave, or second or third, I don't remember. And when we're going to restart again, another problems with the transport, with the workers, so. And however, you were able to do it. You were able to do it. That how do you remember this period? So trying to
very crazy. Yeah, but at the end of the day, the goal was achieved. That was to put everything together, and the important thing is the project outcomes. And essentially, we learn a lot about the process of putting everything together and operating this type of plant, which is really important also. But I mean, at the end of the day, the important thing is to see the reactors working, to see the energy transfer to the power block, and this was achieved at a certain level. So we are happy to have been able to make it flow to the end. No, it's just something that was difficult, but when it passes, it's just fine, you know?
Absolutely, we have learned, but it's curious because, for instance, there has been a lot of critical moments, and we have survived to them, and we have passes. But I remember the part of construction. Well, one important issue for those that are external to the consortium is that, for instance, with this COVID-19 waves, partners were not allowed to travel. So there were components that we must be installed here completely on remote. So,
yeah. I mean, there is a picture of Carlos Tejada on top of the structure with a computer, the telephone, talking to somebody else, I don't know where. So it was really tough. And one thing, if you allow me, that sometimes you think that because you are doing something at a very small scale, it's going to be easier than at the higher scale, and this is not true. I had some issue with the connection, I think.
No, we hear you.
Okay, nice. So what I want to say is that for the scale up, you're going to have problems in some equipment. For the very small laboratory or a pilot plant of kilowatt scale, you're going to find other problems. So it's not easier because you have a lower scale. It's that you're going to find the problems that at the low scale has, and then you will find the problems that the scale up has. So we shouldn't be stopped by some things that we have found are difficult at this scale, because probably they will be solved just having bigger things, you know, like the thing we talk about, the blocking of the particles and things like that. So this is something that should be taken into account.
Yeah, I fully agree. And following your comment, talking myself regarding the operation. So, for instance, when we started the operation at the beginning, the things didn't work. And that's the moment you say, oh, everything is not right, something, how we are going to solve. But we learned that how to deal with the materials, residence times, temperatures, control. And I remember perfectly in the middle of August, the hot heat wave in Seville, everyone working in the calciner and the carbonator, trying to understand what was happening. At this moment, it looks something almost impossible, but we follow, as it has been shown by Carlos Ortiz before. By the end of August, things started to be nice. It's important also to describe how we operate. We operate along the day in the calciner, in the carbonator, and then someone from CSIC, usually Nabil Mohamed, came to collect all the the samples that we have taken, and he take them to the CSP laboratory, and they make the analysis in the CSIC laboratory, and then they gave us feedback from the operation to the next day. So it was a continuous. So they spent in the CSIC long periods waiting for our samples to give us feedback for the operation of the next day. It was really exciting. It was really exciting. And before opening the floor to questions, then thank you all of you for your hard work, for your participation, and also for the enthusiasm for along these 4 years. It has been really a pleasure to share with you all this time. And of course, we are saying this because it's the final info day, but we have a lot of other meetings. So we will have the opportunity to meet. Okay, so now I open the floor to questions, if there is any. Well, I don't see any question, so it's 1 in the afternoon. Oh, please, Irha.
Yeah, I would like to add one more comment, and Juan mentioned earlier the costs for the installation, the costs for the technology. And of course, it is correct that the technology needs to be as cost effective as possible. But I think we have to keep in mind that if we compare our technology with technologies based on fossil fuels or fossil energy sources, we always have to keep in mind that the climate protection is an issue that is not considered in prices for fossil fuel technologies, or it's just getting started that we have to pay a price for the ton of CO2 we are emitting in a technology. So we should not be scared by these costs. I'm pretty sure if the technology further develops and we come really to more efficient unit operations and a better performance of the entire system, and I think a bigger scale will help to have this. I think this is the way we have to choose. If we just say climate change is, or let's say fighting climate change is too costly, then this will be, from my point of view at least, not the right approach for the future.
Okay, thank you very much. Thank you. I don't know if there is any other questions. Well, okay, thank you very much. It has been a pleasure to be with you today, and thank you very much for the great work. So with this, we finish this info day, and okay, we will meet soon in the final meeting of the project and online also. It's a pity, but one important thing. Please, any of you that wants to pay a visit to the installation, of course not the partners, but also external who wants to pay us a visit, do not hesitate in writing me, writing us as consortium. We are fully available for visits and discussion and to show the technology and the things that we have done. Okay. Thank you very much. Have a very nice day.
Thank you.
Okay.
Thank
Bye.
you.
Yeah.
Thank you. Bye.
Thank you, Angela. Everyone that was attending today will share the presentation, and also the video will be available in our different social media. So thank you everyone. We keep engaged for future development and future collaboration. Thank you.
Sure.
Thank you,
Okay.
Angela.
Bye.
Bye.
Bye.